Alright everybody, let's see if the stream's going. Yes, the stream's going. Okay, so we learned our first lesson today about streaming video, which is that while it's better for a lot of reasons for what we're doing with this course than recording a video, if your internet connection isn't strong enough, sometimes it drops out. So the internet dropped out halfway through this first lecture, this first lesson 1.a, and so I have to re-record it because it missed about 10 minutes. And they're kind of important 10 minutes given the mistakes I have people usually make. So we're going to go through it again. This is lesson 1.8, Redux. So to go over this, at the end of it, you're going to be able to recognize the different elements of a polynomial, and essentially you're going to know what a polynomial is. Expand a polynomial, so you're going to be able to do algebra to it. You're going to be able to recognize its degree and know what we mean when we say degree, and you're going to understand what we mean when we talk about the name of an equation, and distinguish between a name and say an equation. So you'll understand what we mean by a name of a expression. Okay. Also, I just erased most of the notes I made before, and we're going to write over them just to save a little bit of time. So, all of these expressions here are polynomials. They're all polynomials. It's supposed to be a pi. So a polynomial is an expression. It's not an equation, it's an expression. There's no equal sign. The way it works is it's made up of a whole bunch of terms that have been added or subtracted from each other. So 2 minus 3x, or 5x squared minus pi. You know, there's very little limit to what you can do, and polynomials are one of the most powerful types of mathematical expressions. They're so commonly used. They're just all over the place. They're just absolutely great. Okay, so what makes a polynomial a polynomial? How can you tell if you're looking at a polynomial or if you're looking at some other thing? Well, like I said, polynomials are made of terms that are added together, and each of the terms satisfies a certain pattern. It looks like some number times x, the variable, to some power, n, another number. Okay? So we call this number out front, we call it the coefficient, and we call this number up here the exponent. Okay? So essentially, the way you recognize whether you're talking about a polynomial is somebody gives you an expression like that, and you're going to break it up into terms that are added or subtracted from each other, and you're going to ask yourself, do each of these terms satisfy this descriptor? By the way, this coefficient can be any number, but the exponent here can only be a whole number. It's got to be positive. So 0, 1, 2, 3, 4, any such numbers. Oh geez, my computer just burped. Gross. Okay. So essentially what we're going to do is somebody gives you an expression like this, and we're going to look to see if each of these individual terms fits this description. So what about that term? Yes, this coefficient of that term is 7.2, and the exponent is 3. So we're good. It fits the pattern. What about that one? The answer is yes for that one. The coefficient is 4, and the exponent here isn't written because it's 1. There's no real reason not to, but generally speaking, whenever the exponent is 1, we tend not to write it. You just leave it off. If it doesn't have an exponent, you just assume the exponent's 1. What about this term? The coefficient here is definitely 14, but there's no variable. This term is called the constant. And we do say that it fits this pattern. We say it fits the pattern because if there were a variable, it would have, or rather, we can consistently write it as having a variable if the exponent of the variable is 0. Remember that any number, say 4 to the power of 0 is equal to 1. We just say, oh, there's an exponent there. We can't see it because its power is to the power of 0, and that means that it just has the value 1. Okay? And so as a result, it doesn't get written in. Okay. Polynomials of all stripes tend to fit a certain form. If everything I've told you about the pattern that all polynomials satisfy, if that made sense to you, then we're golden. We're going to talk about something called the general form of the polynomial, but there's no information. All I'm doing is I'm going to try to expose you to a little bit of mathematical notation. Mathematicians use a very specific shorthand to get their point across without having to use words as often as possible. And so there is a form called the general form of the polynomial that explains all of these points I just made here, only symbolically. And I want you to see it because it's important to accept the, the symbols we use in math. The general form of the polynomial is often written like this: a to the n times x to the n, a n minus 1, x n minus 1, a n minus 2, x to the n minus 2, plus dot dot dot, plus a to the 3, x to the 3, a to the 2, x to the 2, a to the 1, x, plus a 0. Okay? So we call this the general form, and all it is it's a template. It's a pattern. N is a whole number that's bigger than 0. And we say that any system that satisfies this, any expression that satisfies this, is a polynomial. So this is me just saying, repeating everything I said, but numerically. And the reason I wanted you to see this is that it's got some really interesting things here. The n's up top here, these are exponents. So if it's a 3, it means take this number, multiply it by itself 3 times. If it's a 2, it means take that number, multiply it by itself twice. The n minus 2, n minus 1, n, what we're saying is put the highest number on the left-hand side. But these numbers say essentially, well, x could be to any power, and so we're expressing the idea that x could be a really high power, essentially. So they're all powers. They all refer to a procedure that you could do to a number, an operation. These n's down here don't refer to any operations. They're what we call labels. A n minus 1 is the name for the coefficient of the term that has x to the power n minus 1. Essentially, it's a way of labeling things. We could have gone A, B, C. We could have gone, this one is A, this one's B, this one's C, this one's D, etc. But this, if you ran out of letters, what would you do? Using numbers in this way, it allows us to assign labels to keep everything straight in a way that goes up to infinity if we want. So like I said, there's not any new information that I didn't explain up top here in this general form. I just want you to see as early as you can in this math course some of these mathematical expressions that we use to some of the shorthand mathematicians use. That's called an index and a label. Okay, so let's do an exercise just as a way of sorting out all the things we just talked about. So somebody might give us a polynomial and ask us what all of these different coefficients are. how do we figure out what they are? What we're going to do is we're going to look at our expression and we're going to match it and write the coefficient. Okay, so for instance, a2, let's start with that. That's the coefficient of the term that has x to the power 2. So it's minus 4. A to the 3, this one, it's the coefficient of the term that has a 3 up there. So it's equal to 8. A to the 1, that's the term that has x to the power 1. Oh, remember, when it's x to the power 1, we don't write 1. So call that minus 13. A to the power a to 0, that's the constant term. It's that one right there. Remember that we could have written that x to the power 0, but it's the same thing. All right. What about these higher ones? Are there any of you that we haven't included? That one, x to the 5. So that's minus 2. What about a4? There's no term in this expression that has the power x to the 4, so that coefficient's 0. Similarly, there's no term that has x to the power 6, so that's 0. There's no term that has x to the power 7, so that's 0. No term that has x to the power 8, so that's 0. And arguably, I could just extend this list forever. Okay. Let's move on. The neat thing here is that, one neat aspect to this is that sometimes you don't get polynomials that quite fit the general form. Okay? So for example, this one here doesn't fit the general form. And the reason it doesn't fit the general form is that, well, for one thing, there's 2 x to the power 2. Essentially what this is 2 different polynomials added together. That'll give me another polynomial, but the first thing I want to do is something called expand it. I want to get rid of the parentheses and reduce it down to its simplest form, where there's only one term that has an x to the power 2. There's only one term that has x to the power 3. How do I do that? Well, I can start by getting rid of these parentheses. So it's x4 plus 3x squared minus 2x plus 2. And that one, x to the 7 minus x to the 3 plus x squared plus 1. And then what I want to do is I want to combine them into one list. So I'm going to move all the larger ones to the left and the smaller ones to the right, exponent powers. So let's see, I'll move x to the 7 over here. Is there an x to the 6? No. X to the 5? No. X to the 4? Yeah, there's an x to the 4 here. X to the 3? Oh, there's one over here. Any x to the 2s? There's 2 of them. X to the 1? There's only one of those. Okay. Now I want to continue simplifying it. The deal is that I can combine some terms, like 2 plus 1, what's that equal to? That's equal to 3. In a similar way, I'm able to combine the terms that have the same x to the power exponent. So these are both x to the power 1, and so I can combine them together. So this one has coefficient 1. 1 minus 2 is minus 1 to the x. 3x squared is all alone. I thought there was 2x squares here. There were 2x squares here. What did I do? I made a mistake. I made a mistake copying things out. Let's see. X to the 3 is there. X to the 2. Yep. So this is supposed to be x squared. Alright. So these two become plus 3. This is alone, so it's minus 2x. There's 2 of these. 3 plus 1, so now there's 4 x squared terms. That's the next one's on its own. 7x. We call this the completely expanded form Nice thing about an expanded form of a polynomial, it's really easy to interpret. And so we use expansion, which is a verb, to essentially combine different polynomials together and get one complete one that's easy to interpret. These two polynomials have been multiplied together. So what do? I want you to be really careful with learning how to do the following expansion, because it's something a lot of people make mistakes in higher levels. It's one of these things where if you don't quite understand, you are going to make a lot of mistakes in the future, and your life will be more frustrating than it needs to be. So this particular expression is a shorthand for a procedure. Essentially, what this is shorthand for is we're multiplying this term by both of these terms, one after the other. Okay? So I want to rewrite this expression. First I'll write it as 3x squared times 4x minus 1, and then 2 times 4x minus 1. Multiply this out now. 3x squared times 4x minus 3x squared times 1 plus 2 times 4x minus 1 times 2. Now you've done this, you can multiply each of these like that, which is what I just wrote out. And now that you've multiplied each of these terms, you can combine them. So these terms, their coefficients multiply together, and then these two, x to the power 3. This is just multiplied by 1, so it's going to stay exactly the same. 2 times 4 is 8, and 1 times 2 is 2. And then I have the completely expanded form. Okay? There's all sorts of shortcuts that people can take, and a lot of people try to do it in their head. But if you pick up bad, if there's some aspect to this expansion that you don't understand, you will make mistakes, and a lot of the reasoning that people do in the future won't make much sense to you. So I would prefer if, at least for the first little while, every time you multiplied things out, expanded them, you did it in this way, writing out each step and then multiplying it in the following way, breaking down each into individual components. It'll make it easier for me to understand if you understand. So let's do another example. Here, I want to move this one up. There we go. Let's expand this out. I'm going to multiply this expression with each of these terms one at a time. So it's 3x squared times 4x plus 6, and then 2x times 4x plus 6, and then 1 times 4x plus 6. Now that I've done that, I want to multiply each of these terms together. Each of these terms together. Be really careful with signs. Each of these terms together. Okay, let's do it. So it's 3x squared times 4x plus 6 times 3x squared minus 2x times 4x minus 2x times 6. Be really careful with these signs. So minus 2x, so then minus sign. Okay. Plus 1 times 4x plus 1 times 6. And now I can simplify them. 3 times 4 is 12, x to the 3. 6 times 3 is 18, x squared. 2 times 4 is 8, x squared. 2 times 6 is 12x. 4 times 1 is 4x plus 6. And now, there's still multiple terms that have x squared. There's still multiple terms that have x. So I need to continue simplifying, combining these ones together. 12x to the 3. So it's 18 minus 8 is 10 x squared. And 12 minus 4 is minus 8x plus 6. And then I'm done. One method that you might have learned from high school that they often tell students is a shortcut, actually. It's a recipe called FOIL, F-O-I-L, which stands for first, outer, inner, last. It's a shorthand way of memorizing which terms to combine, and it cuts out some intermediate steps. So in this case, by first, we mean these two, the first in their order. It says multiply those together first. 2x times 5x. Then multiply the outer ones. This one and this one are the outer ones. Minus 1 times 2x. Then multiply the inner ones. This one and this one are the inner ones. 3 times 5x. And then the last ones, which are that one and that one. So it's plus 3 times minus 1. And then you simplify them. 10x squared minus 2x, 15x minus 3, and then you finish simplifying them. You combine the similar terms. 13x minus 3. All done. Alright, so let's try a really big example before we go any further. Essentially, it's really important to me that you're able to expand these properly. This is in part because, well, I want you to get the right answer, but in huge part because this is a big stumbling block that a lot of people have in understanding the arguments that we'll be explaining to you in university math. And it's an unfortunate stumbling block because it's not a very difficult skill to master. But you know, for whatever reason, people sometimes forget how to do it, or maybe they misunderstood from the start. Regardless, I'd like you to do it the long way, write it out as I have been, just to make sure that you're getting it right. So this first term, we're going to multiply all these together first. This by this, and then that by that. Okay, so watch. 4x. Oh, yeah, that reminds me. I don't really like FOIL. You're going to hear me to tell people when they're expanding these to FOIL them out, because I recognize that this lesson is ubiquitous. But thinking of this operation as a procedure where you just follow some steps isn't quite... It makes math seem a lot more complicated than it actually is. I mean, really, this is just a fairly simple algebraic operation that you should understand how to do. And so if you're kind of using a recipe to do it instead of just brute force pushing your way through the algebra, it makes your algebra... It means you're practicing algebra a little bit less, and also it's kind of... it's easier to make mistakes. So for the time being, I'd prefer if you spelled everything out, and then in terms of the intermediate steps, just because it's easier for me to find the mistakes that you might be making and cure you. So the second one's 2 times 3x squared minus 2x plus 1 plus 2 times 3x squared minus 2x minus 2. Then I'm going to multiply all those together. So it's 4x times 3x squared minus 2x times 4x plus 1 times 4x plus 2 times 3 times x squared minus 2 times 2x plus 1 times 2 plus 2 times 3x squared minus 2 times 2x minus 2 times 2. Now combine them all together. 12x to the 3 minus 8x squared plus 4x plus 6x squared minus 4x plus 2 plus 6x squared minus 4x minus 4. And now I need to simplify things. So I'm going to start by reordering this. Essentially I want to group together the ones with the like powers. So 8x squared, any other x squareds? Yeah, there's a 6x squared, and then there's another 6x squared. Now x to the power 1. 4x minus 4x, any others? There's another minus 4x. And then constants. Plus 2 minus 4. So let's combine these together. 8 minus 8 plus 6 is plus 4x squared. 4 minus 4 minus 4 is minus 4x, and then 2 minus 4 is minus 2. And I'm done. Okay, so being able to expand polynomials, expand and simplify polynomials, it's an underrated skill. It's equivalent to like walking if you're gonna play a sport, which is to say that if you can't do it, nothing you're gonna do is gonna be very good. And also, it's not trivial. Don't let anybody tell you that this is a simple thing to master. It's something that takes some time. It's something that takes some diligent effort and some mindful effort. That said, you can do it. There aren't too many moving parts in this particular thing. If there are any aspects of it that don't make sense, please talk to me about it, or talk to somebody else. Yeah, let's move on. So, the most important thing, we classify polynomials. Oops. It's something that we do, and it's fine. We classify them according to their behavior, and one of the most important indicators of their behavior is something called the degree. So I've got a few examples written out here. This first one is degree 5, and the first one's degree 5, this one's a degree 12 polynomial, and this one's a degree 3 polynomial. Try to figure out what about it makes it a degree 5 or a degree 3 or a degree 12. Let's see if you can figure it out. I bet you can. Maybe pause the video and make a guess. Well, let's tell okay, so it's obviously not the number of terms in it, because none of the terms have 5 terms. None of these have 12 terms, right? So that's not it. It's not the coefficients. What else could it be? I mean, so like 5, for instance, isn't a coefficient in this expression. 5's one of the exponents. And 12's one of the exponents in this one. And 3 is one of the exponents in this one. What's the significance of 5, 12, and 3 in each of these? It's not the term that's most to the left. 5, 12, and 3 is the largest exponent. The degree of a polynomial is the largest exponent it has. Okay? Or arguably the largest exponent that doesn't have a coefficient that's 0. You don't write those. So the first one is a degree 5 polynomial because its highest exponent is 5. The second one is a degree 12 polynomial because its highest degree is 12, etc. Okay? Degree is something that's actually pretty important. It shows up in a lot of things, and you can definitely sort polynomials based on how they behave, and that sorting corresponds to what the degree is. Alright, last thing. Naming polynomials. This is actually a topic that is part of a much broader topic. It's super important, but it's also something that students often kind of get wrong in really interesting ways. So your boss brings a list of polynomials to you, right? And you want to talk about them. Let's say they say, hey, we want to talk about their degrees. How do you do that? Like, okay, so you're like, well, this one has degree 3, and your boss is like, well, which one? And you go, this one here. And your boss says, well, I can't see the paper you're pointing to. And then you go, oh, it's the one on your paper that says x to the 3 plus 4x minus 2. And your boss goes, oh, okay, I see it. Right? Do you see what I'm saying? It's important to talk about polynomials, and it's important to describe them, and it's important to characterize them. But when you do so, writing out the entire polynomial takes forever, and describing the polynomial to another person also is very onerous. So instead, we do the same thing as we do to people. There's a whole bunch of them, but we give them all names. And usually it's a letter of the alphabet. Call this one F, call this one G, call this one H, call this one S. Okay? When you're naming a polynomial, though, you don't just write a letter. You write the letter and then a parentheses, and X, parentheses X, parentheses X, parentheses X, like that. Okay? So the tradition here, it's a shorthand actually, and it's actually a pretty useful tool, is to write it, the name of one is, there's a letter, that's the polynomial's name, and then there's a set of parentheses, and then between them there's a symbol, and that symbol is the name of the variable. In all these cases, it's X. And so when somebody describes a polynomial to you, they'll say, hey, polynomial h of x. You know a couple things about it. One, you know that it's h, so I guess they're talking about that one there. But another thing you know is what the variable is. Okay, so before we go any further, I want to emphasize the difference between an equation and an expression. We said before that polynomials are expressions. What's with this equal sign? Is this an equation now? And the answer is not really. I guess technically it is us saying that these are equal, but only as so far as, you know, you point at me and say, that's Ben Tippett, that one there. The equal sign is us just pointing at the thing, pointing at the equation and saying, this is its name. That's what the equal sign means in this context. And so there is never a case when we'll ask you to solve this equation. That's not the type of argument we're making. So no one's ever going to say, oh, okay, rearrange this, x plus 2 is equal to x to the 3 plus 4x. No, you'll never have to do that kind of thing. There's no information like that in this expression. All we're doing is we're saying, here is an expression. This thing is the shorthand name of that expression. Okay? There's an equal sign in there. There definitely is, but that doesn't really make it an equation. All we're doing is we're naming the expression. Okay? How do you know when it's happening? Well, usually at the very start of a problem, when we're giving you the polynomial that we want you to work with, we'll say, here's a polynomial. And then further down the problem, when we're talking about using the polynomial, we'll say, hey, use the polynomial in the following ways. Find out where it's 3, or something like that. We'll make arguments involving the polynomial by its name, rather than spelling out each individual term. Okay? So that's the naming convention. It's called function notation. Don't forget the parentheses and the x. They don't mean anything. Well, I mean, they do mean something, but it's not like it's just the name of the variable. So yeah, don't get confused with it. It's not an equation we're asking you to solve. All we're doing when we write this is we're just giving the function a name so that we can talk about it without wasting our breath and spelling everything out. So as a demonstration and an exercise, let's try this. Here are 3 polynomials. I've given them all names, and I say, hey, let's do things with these polynomials. Find a0, a1, a2, a3, a4 for this polynomial. Which one is that? It's that one there. Well, a1, a2, a3, a4, those are coefficients, but usually when we use them in polynomials, we're referring to one that's been completely expanded. That one hasn't been expanded, so I first need to expand it. So let me expand this out. So this is x times x plus 1 minus 1 times x plus 1 plus 3. So this is x squared plus x minus 1 plus 3, which becomes x squared plus 2. All right. So a0 is equal to 2. It's a coefficient. a1, there's no term in this that's x to the power 1, so its coefficient must be 0. a2, its coefficient's 1. But there is no coefficient. Yes, there is. We just don't write that one. a3, that's 0. a4, that's also 0. What degree does polynomial h of x have? Well, degree is also something that we usually talk about in terms of a fully expanded polynomial. So I need to start by expanding that polynomial. So let me do it. 3x, x minus 1, plus 2 times x minus 1, plus 2 times 4x plus 1. Alright, so then that's 3x squared minus 3x plus 2x minus 2 plus 8x plus 2. And then put them all together. So this is 3x squared, now all the x to the power 1 terms. Minus 3x plus 2x plus 8x minus 2 plus 2. And then so this is 3x, stuff's poking up, 3x squared plus 7x plus 0. Alright, so this is degree 2. Alright, time for our review. What did we talk about? We had lots of fun today. I have been recording videos for about 6 hours straight. So, polynomials are expressions that are made up of different individual terms. Each term has a variable to an exponent power, and each one's multiplied by a coefficient. And they're all combined together to make one large expression, terms added together. They have several different forms. There's the completely expanded form, and then forms where we write a polynomial in terms of smaller polynomials that are all multiplied together. Those are called factored forms. Polynomials are often described, so you can describe a polynomial algebraically using a factored form or expanded form. But one way to describe its qualities is to talk about its degree, which is the highest number exponent. The easiest way to tell what the degree is to look at it at its completely expanded form. And then another aspect of this is something called roots. We're going to talk about those more in future lessons. All right, good luck. Have a good time.